gravitational clustering that leads to structure formation. But it turns out that when it comes to predicting the shape of the halo as well as the substructure that's present in that halo, there are some discrepancies between the predictions that are derived from lambda CDM and the observations that have been made. And these discrepancies are called the small-scale challenges to lambda CDM, and they amount to basically a discrepancy between predictions derived using complex computer simulations and then these complicated observations of the halos and of dark matter, of what happens in like halos around galaxies. A famous example of one of these small-scale challenges is the missing satellites problem. According to simulations based on lambda CDM, galaxies should have a relatively high number of satellites in their dark matter halo. And those satellites are things like dwarf galaxies or globular clusters. But observations suggest that, in fact, the Milky Way doesn't have that many satellites, like way less than is predicted based on the simulations. And so this is one example of this kind of small-scale challenge to lambda CDM. Now, it's an open question how to respond to these small-scale challenges. In a separate paper, I've argued with Nora Boyd that the small-scale challenges don't warrant any kind of abandonment or modification to lambda CDM. But I do recognize, right, that these small-scale challenges show that something is not well understood. It might be the computer simulations, it might be your observations, it might be something about dark matter. Like there's something on subgalactic scales that we don't quite understand yet. So that's the first set of problems about dark matter. A second set of problems or questions about dark matter focuses on the supposed individual entities that constitute dark matter, that are responsible for the collective behavior of dark matter. And so this is why dark matter doesn't just take central stage in astrophysics and cosmology, but also in current particle physics. In the 2020 update to the European Strategy for Particle Physics, the quest for dark matter is listed as one of 4 other essential scientific activities for particle physics. The other here indicates that these essential activities are not directly focused at building a new accelerator. But basically, right, the quest for dark matter should be a major focus for particle physics, says this European strategy. Now, in the philosophical literature, there are, the discussion of dark matter is young, and there are a few papers on the epistemology and the methodology of searches for dark matter particle candidates. I'm thinking here in particular of recent papers by Schreer and by Antoniou. But the epistemology of cosmological and astrophysical research into dark matter, which aligns with this sort of first set of open problems that I mentioned, is less established in philosophy of science. And so my goal in this talk is basically to make some headway into proposing a general epistemic framework for how we might think about how cosmologists and astrophysicists research the dark matter problem today. Before I go on, I should flag here that there's been some work by Michael Weisberg and Melissa Jacquard, but that's focused specifically on the dark galaxy hypothesis, and so I won't focus too much on that today. So there's 3 claims that I'm going to try and establish today. First is that astrophysical dark matter research essentially relies on so-called local eliminative reasoning. And this idea of local eliminative reasoning is something that I'm going to draw from Abelson's recent paper. The second is that astrophysical dark matter research tends to be multi-purpose, which means that it's researching more than one target at the same time. And that implies that astrophysical dark matter research can contribute to progress on more than the dark matter problem alone. And finally, the success conditions of astrophysical dark matter research are broader than usually recognized, but there are some important limitations that I want to address. And so I'm going to proceed for the rest of the talk. As background, I'm going to start by distinguishing 2 dark matter concepts. And this distinction between these 2 dark matter concepts is basically going to be important as a setup for the rest of the talk. I'll then show that research into astrophysical dark matter essentially relies on local eliminative reasoning. Then I'll argue for this multi-purpose nature of astrophysical dark matter. And here I'm going to use the case of stellar stream research to investigate this multi-purpose nature. And then I'll consider some limitations to astrophysical dark matter research, and then I'll conclude. So let me start with these two dark matter concepts. So in general, I believe that in order to properly understand the epistemology of dark matter research, it's important to recognize that there are two different dark matter concepts at play in scientific practice. And different types of dark matter research are informed by a different kind of dark matter concept. These dark matter concepts I'm going to call astrophysical and fundamental dark matter. Let me stress, these names of astrophysical and fundamental dark matter are just things that I came up with because I had to label it. I don't mean to imply anything deep by using the word fundamental or anything like that, right? So the first kind of dark matter concept that I think we see in scientific practice is astrophysical dark matter. And that can roughly be defined as a form of non-baryonic matter that behaves as a collisionless fluid, is slow-moving, that's what the cold refers to. It doesn't interact electromagnetically, it can only interact minimally through the strong interaction, and it constitutes 27% of the current energy density of the universe. Now, this astrophysical dark matter concept is the dark matter concept that emerges out of cosmology and astrophysics. It's this dark matter concept that's informed by and based on observations of the CMB, of structure formation of the bullet cluster, all of these things that I was mentioning before, right? So this cosmological and astrophysical observations, they provide evidence for the existence of this astrophysical dark matter. In contrast, fundamental dark matter is any specification of a constituent of dark matter. So that means any particle or any entity, because it could also be primordial black holes, say, that satisfy the conditions that are laid out by astrophysical dark matter and that further specify some of the other properties of dark matter, right? An example here, for instance, are WIMPs, weakly interacting massive particles. WIMPs collectively satisfy all of these properties that astrophysical dark matter describes, but in addition, they say some further things about the fact that dark matter interacts through the weak interaction, for instance, right? So this is the basic distinction that is, I think, at play in science, and that informs different types of scientific research, right? And especially fundamental dark matter, that concept is behind a lot of the searches for dark matter candidates, like WIMP searches or production experiments at the LHC. Now, this distinction, to sort of illustrate that I think it's really part of scientific practice, is present in the scientific literature. Here's an excerpt from the Particle Data Group and their entry, who writes this review on particle physics. And here's what they say in the opening paragraph of their entry about dark matter. They say, modern cosmological models invariably include an electromagnetically close to neutral, non-baryonic matter species with negligible velocity from the standpoint of structure formation, generically referred to as cold dark matter. For the benchmark lambda CDM cosmology, adopted in the cosmological parameters, that's a different part of their review, the dark matter accounts for 26.4% of the critical density in the universe, or 84.4% of the total matter density. Total matter density is the energy density budget without dark energy, basically. And so this first part is more or less what I refer to as astrophysical dark matter. But they continue that first paragraph as follows. They say, the nature of only a small fraction, between at least 0.5% and at most 1.6% of the non-baryonic matter content of the universe is known. That's the three standard model neutrinos. Instead, the fundamental makeup of the large majority of the dark matter is as of yet unknown. And when they say unknown, right, what they mean is that there is a really broad range of possibilities for the fundamental makeup of dark matter. That is, for properties that dark matter could have, in addition to the ones described by astrophysical dark matter, but for which we don't have empirical constraints or evidence right now. And so that fundamental makeup of dark matter is what I refer to as fundamental dark matter. And as another reminder, right, here's what is the relation between astrophysical and fundamental dark matter. This chart, I think, can help. So the black, the purple, the blue outlines all represent possible extensions to the standard model of particle physics. So not that of cosmology, right, but that of particle physics. right? And here the idea is that, in addition to your well-known electrons and protons and quarks, scientists believe that there could be other more exotic kinds of particles out there. And some of those exotic particles that could be out there could also constitute dark matter. But not all proposed extensions to the standard model of particle physics qualify as dark matter, right? And so which ones count as dark matter candidates? That's determined by the astrophysical dark matter concept. In other words, the astrophysical dark matter, right, the dark matter concept that we get out of cosmology and astrophysics, sets the boundaries for the space of possibilities for fundamental dark matter candidates. And that space of possibilities is highlighted here in this red shaded region on this plot. And so candidate fundamental dark matter concepts are points or regions within that space of possibility, so within that red shaded region. Okay, so astrophysical dark matter sets the space of possibilities, fundamental dark matter candidates pick out, or astrophysical dark matter sets the boundaries, not candidates, just astrophysical dark matter. Fundamental dark matter candidates pick out regions or points in that space of possibilities. Okay, so that's sort of background. Now, what I'm going to focus on today is this research into astrophysical dark matter, right? It's that first set of problems, for instance, that's relevant here, right? The idea of small-scale challenges, making progress on the small-scale challenges, means making progress on the astrophysical dark matter concept. And so let me zoom in now on research into astrophysical dark matter. And the way I want to do this is by looking at one of the most famous lines of evidence for dark matter, the bullet cluster. So here's an image of the bullet cluster. It's in fact a merging event between two clusters of galaxies, where one looks like it's moving as a bullet through the other. That's where its name comes from. And famously, scientists were able to map out where most of the ordinary matter is, or baryonic matter, and compare that with where most of the gravitational mass is in the bullet cluster. And the pink shaded regions highlight where the ordinary matter is, and you see that it's mostly centrally located. So this is where most of the hot gas is. And they observed this through X-ray observations, right? But the scientists who observed the bullet cluster were also interested in figuring out where most of the gravitational mass is. And they determined that through gravitational lensing of the background galaxies. And what they found was that the gravitational mass is primarily located in the blue shaded regions. And clearly you can see from this image that the two don't line up, right? The blue shaded regions are on the outskirts, the pink shaded regions are in the center. And what this shows is that there has to be much more gravitating mass than there is like ordinary matter in the bullet cluster. And so this result is extremely robust to changes in the assumed theory of gravity, meaning that this result of this displacement between the gravitating mass and the ordinary matter does not actually depend on general relativity specifically as a theory of gravity, right? And so therefore, the scientists who made these observations claimed that the bullet cluster provided direct empirical proof for the existence of dark matter. That was a quote. And that was a quote from their paper title. Okay. So this is what the bullet cluster is. Now, if we look at how they finally reached that conclusion in the discussion section of the paper, it turns out that, in fact, they didn't immediately conclude that their observations showed that dark matter exists. Rather, in their discussion sections, the author go through several alternative explanations for their observations, and they exclude them one by one until there being dark matter is the only one that remained. And so the first kind of example of an alternative explanation for the results of the bullet cluster that they consider is there being masses in the line of sight that basically distort the gravitational lensing picture. And they exclude this based on probability estimates for the presence of structures that would have the right lensing strength, but that would not otherwise have been detected. So they're just like, it's super unlikely that there would be masses of just the right size that would just be in our line of sight so that it looks like it's the bullet cluster that's doing the lensing, but it's in fact not. Like probability estimates just make that very unlikely. They use the same kind of reasoning to exclude that there's large filaments in the line of sight. Finally, they also consider alternative theories of gravity, right? Because, and here they say, they exclude this, but now they exclude this based on the fact that any alternative theory of gravity would still require the presence of dark matter to account for the bullet cluster results. That's what I meant when I said the result was extremely robust. And so this is why the authors conclude that indeed there being dark matter present in the bullet cluster is the only possible explanation for their results, and therefore the bullet cluster provides empirical proof for the existence of dark matter. So in and of itself, I think the reasoning in the original paper about the bullet cluster shows the reliance on eliminative inferences in dark matter research. But I want to go a little bit further now and like hone in a little bit more on this eliminative reasoning. And the first thing that I want to say is that I actually think that this reliance on eliminative reasoning is an essential feature of astrophysical dark matter research. And the reason for this is that any individual inference from an observed phenomenon, like the bullet cluster observations, to the presence of dark matter has to reckon with the fact that there is only gravitational access to dark matter. So for any single phenomenon like the bullet cluster, the only way we can detect that dark matter is there is through its gravitational effects. And that implies that in order to conclude that those gravitational effects are really there and were really caused by dark matter, all other possible explanations for those gravitational effects have to be eliminated first. So that's where I think this like essential reliance on eliminative inferences comes from. And so if we take that, right, if I'm right that astrophysical dark matter research really does have to rely on eliminative inferences, the next question is, well, okay, what do these inferences look like? And here, I think that Shannon Abelson recently published a paper that is really helpful in illuminating the structure of these inferences. And she describes something called local eliminative reasoning. So what is this local eliminative reasoning according to Abelson? First, Abelson stresses that local eliminative reasoning is not the classic image that we tend to have of eliminative reasoning, a la Newton. According to this classic image, right, scientists have a set of observations. They come up with all possible hypotheses that could explain those observations, and they then make additional observations so that they can exclude hypotheses one by one until one of them remains. Abelson says that this is not the image of like how local eliminative reasoning works. Instead, Abelson describes local eliminative reasoning as being model-based. So it's not about identifying isolated individual hypotheses and directly comparing them to observations, right? Instead, local eliminative reasoning is model-based. The focus is coming up with empirically adequate models that can be enriched with additional variables or other modeling assumptions that can improve their empirical adequacy. Right? So the elimination that is happening is between different modeling components that we could add to our pre-existing model of a system that we have, right? And so, for instance, in the case of the bullet cluster, there is already sort of a model of how the bullet cluster is structured, right? We have a sense of where the galaxies are, where the hot gas is. But then the question is, do we add in this assumption that there are additional masses in the line of sight, or do we change our theory of gravity, or do we add in this assumption that there is a large amount of dark matter present in the bullet cluster? Do we add that to our model? Now, if local eliminative inferences are model-based, Abelson stresses that that means that the eliminative reasoning doesn't happen in a vacuum, right? Instead, she considers them to be holistic, where scientists already have a web of models and established evidence as background knowledge. And so whatever new model assumption that gets introduced, that needs to cohere with that pre-existing web, right? And again, we see this in the bullet cluster case, right? I mentioned that filaments or other masses in the line of sight, that those were excluded based on probability estimates. Basically, what that means is the scientists excluded masses being present in the line of sight because it just wouldn't cohere well with what we already know about our universe and about like the large-scale structure in that universe, right? And so it just wouldn't cohere well with our pre-existing knowledge of how common either masses or like filaments are in the universe. And important here, right, this background knowledge that we can rely on when conducting the elimination, Abelson stresses that background knowledge can be extremely broad. And again, right, in the case of the bullet cluster, we're not just looking at the bullet cluster itself, we're looking at all kinds of systems that could be undergoing gravitational lensing in order to assess what the accurate modeling or what the best modeling assumption is that we can add into our space of knowledge already. And finally, though, while the background knowledge is very broad, the inference is, in a sense, is local. And the idea here is that it is focused on a specific type of systems that is well defined and well described. And because the specific type of system is well described, we know what the relevant background knowledge is. And that background knowledge can then be really broad. And so I think all of these features are present in the bullet cluster case, as I've sort of tried to indicate as I've gone through them. And so given that there's a clear instance of eliminative reasoning, I think the right way of thinking about this eliminative reasoning is according to this idea of local eliminative reasoning, right? And so this is basically the first claim that I wanted to establish. It was saying that I agree with Abelson on the idea of local eliminative reasoning, and I think it's a correct epistemology for astrophysics. And I think we see this epistemology at work in the context of astrophysical dark matter research. And let me stress again, when I say astrophysical dark matter research, I mean research that constrains the astrophysical dark matter concept, right? So let me now focus on the second claim, this idea of the multi-purpose nature of astrophysical dark matter research. And this I'm going to do by focusing on the use of stellar streams and to investigate the dark matter subhalo population of the Milky Way. My goal here is to once again show that we can see local eliminative inferences at play, but I'm going to dig deeper into how they happen and what this might mean about how we think about the success of astrophysical dark matter research. So let me tell you about the case. As I mentioned in the beginning of the talk, right, the behavior of dark matter on subgalactic scales is not yet well understood. And one way scientists have tried to make progress on this is by using stellar streams. Now, what are stellar streams? Tidal stellar streams are astronomical objects that, as the name suggests, are long strings of stars. They originate from, for instance, a globular cluster or a dwarf galaxy, like the ones you see surrounding the Milky Way on this image, right? You see all these dots. Those are examples of globular clusters or dwarf galaxies. The cluster or the dwarf galaxy can be disrupted, and then the resulting stellar stream orbits the Milky Way roughly along the same orbit as the object from which it originated, right? Now, as a recent review paper stated, long coherent stellar streams accreted in the Milky Way halo in the Gaia era, Gaia is a famous satellite for observations, became our most sensitive antenna for dark matter. So we can use these stellar streams to find dark matter, but how, right? In order to play that role, 3 different target systems need to be modeled: stellar streams, the dark matter subhalo population, and astrophysical dark matter. And that is what happens in this paper by Baerdemaeker et al. From 2019. And so I'm going to focus a lot on what happens in this paper. So let me talk about how they go about their research. So the first target that Baerdemaeker et al. Are interested in is stellar streams. And there's 2 goals here. First, obviously, is getting the morphology of the stellar stream right. Right, it's just like having to figure out what the stellar stream even looks like. With that in place, and given that they see that there are some gaps in the stellar stream, the next goal is to identify what caused these gaps in the stellar stream. And Baerdemaeker et al. Identified 2 gaps in GD1. This is the stream they focus on, right, GD1. And at one of those gaps, there's a spur attached to it, basically a group of stars that is like bent backwards at the stream right next at the gap, right next to the stream. And so they see these two or three, but two main ones that they focus on. And the first gap, they say it's associated with a progenitor of GD1, so like with the dwarf galaxy or the globular cluster it originated from. GD1 is a globular cluster, I think. The second gap, however, and the spur that's attached to it, that they think is more interesting and also what I will focus on. And I again believe that this work displays this local eliminative reasoning that I've described just now, because Baerdemaeker et al. Are very systematic. They go through three classes of possible explanations that would be consistent with the behavior of similar systems. So they're like, these are plausible explanations for why GD1 has this substructure. And then for each of these classes, they then evaluate them based on pre-existing background knowledge. They're basically like, is this plausible given what we already know? And this background knowledge is not just of stellar streams, but also of the structure of the Milky Way, of galaxies more generally, and so on. And so I'm going to go through the details in quite a bit of detail, but don't worry if you don't follow all of this, because the main point that I want to get across is that, once again, what we see at play here is that scientists are coming up with many different modeling scenarios that could account for the substructure of GD1, and they then eliminate them based on how well they cohere with their existing background knowledge and evidence. In order to determine whether these modeling assumptions are like plausible explanations, right? And so Baerdemaeker et al., as I mentioned, considered three classes of explanations for the GD1 gap and spur, and these are non-impact scenarios, some luminous objects perturbing the stellar stream, or a dark halo substructure perturbing the stellar stream. So non-impact scenarios would include the fact that the progenitor, so the thing that the GD1 stream originated from, that progenitor somehow had a really complex structure that remained present in the stellar stream when it became disrupted. This they exclude based on the fact that the level of substructure in GD1 is so complex that the progenitor would have had to have a far more complex substructure than any of the currently known globular clusters have. Another non-impact scenario is a chaotic gravitational potential. This is also excluded based on the strong localization of the gap and the spur. So then the two other options are both impact scenarios, like somehow something interacted with GD1 and caused this gap and spur. One option is that GD1 was impacted by a luminous object, right? One that we can detect through its light that it emits. For instance, one of the 50 dwarf galaxies or 150 globular star clusters that are orbiting our Milky Way. Now, thanks to the Gaia mission, Baerdemaeker et al. Are able to determine the orbits of these satellites of the Milky Way and figure out if they ever came close enough to the gap in GD1. And what they see is that the possibility of a collision with GD1 is basically excluded because none of the detected luminous satellites would have come close enough to the stellar stream. I want to say that there is a caveat here that they want to double check this by having some additional type of data, but that's still lacking for 25 of the 50 dwarf galaxies, at least when they publish this paper. But, you know, Milky Way satellites are preliminary excluded, or for now at least. Another form of luminous perturbers, would be that GD1 was perturbed when it crossed the Milky Way disk. So basically, as it moved through the Milky Way disk, that somehow that moving through the disk would have disrupted it. Again, this is not considered, this is the Milky Way itself excluding it is excluded, let me re-say that. The Milky Way disrupting GD1 itself is excluded based on the density of the Milky Way disk. It just wouldn't be dense enough. But they say, look, maybe there was a giant molecular cloud that was hiding in the Milky Way disk that caused the perturbation. Again, they don't consider this highly likely, though the option isn't completely rejected. And again, this is based on the available background knowledge of molecular clouds. So finally, the authors are led to possible so-called dark perturbers. That's a perturber, so like something in the Milky Way halo, that would be made almost entirely out of dark matter. One option are low luminosity perturbers, which would basically be a dark matter subhalo that contains some baryonic matter. That's why it's low luminosity, but not completely dark, but it's very low luminosity. Again, this kind of perturber would have to be hiding in the plane of the Milky Way to not have been detected already. And so they hope to exclude this with more survey data. Another option is maybe it was a primordial black hole, but there's already strong limitations on how many primordial black holes we expect there to be contributing to the dark matter budget. So again, this is considered extremely unlikely. And so finally, what they end up with is a possible encounter with a dark subhalo. That is like a subhalo in the Milky Way halo that consists entirely out of dark matter. And although I'm skipping quite a lot of detail here, right, the authors conclude for dark perturbers that within the boundaries of lambda CDM, it is broadly to be expected that GD1 would have encountered a dark matter subhalo on its journey throughout the Milky Way halo. And moreover, such an encounter could have caused the gap and spur that they've observed in GD1. And the way they go about this is by modeling such an impact scenario through simulations, and then they like sort of look at different properties of whatever it is that perturb the stellar stream, and they look at the possible scenarios that can lead to the observed spur and gap. And so it turns out it's possible that a dark perturber could have caused the gap and spur in GD1. And since all the other explanations have been excluded, right, they submit that it's probably likely that it was a single dark perturber. I mean, not all of them have fully been excluded, but you know, it is likely that it was a single dark perturber that caused the impact on GD1. And so this is the end of sort of the local eliminative reasoning that I wanted to describe for you, right? And I want to stress here again that it seems crucial and inevitable in this context, because if it really is a dark perturber that caused the gap and spur in GD1, there's not really going to be an option to do an electromagnetic follow-up. There may be a possibility to do a weak lensing follow-up, but there's not going to be sort of electromagnetic detections of this subhalo, right? And again, the eliminative inferences that are happening here are local and highly informed by existing background knowledge of the Milky Way, of stellar streams, of satellites of the Milky Way, and so on. Now, this was like the first target that's being constrained. It's like the stellar stream and what explains the look of that stellar stream. But if it really is a dark perturber that has caused the spur and gap in GD1, so if the local eliminative reasoning holds, that means that the stellar stream observations can provide evidence for the existence of dark matter subhalos. And this is what Bonacca et al. Conclude their paper with. They write, further study of the GD1 gap and spur feature may provide the first opportunity to follow up an individual halo substructure. But most excitingly, these features demonstrate that cold stellar streams are extremely fine-tuned detectors, sensitive at a level that was only hoped for beforehand. In addition to GD1, there are over 40 known streams in the Milky Way halo. In the era of Gaia, we now have both the incentive and the resources to study them all in detail, and with a full network of streams, we could learn not only about individual halo substructures, but about the population as a whole. So what GD1 is doing here is it's being used to constrain a second target system, right, which is the dark matter subhalo population of the Milky Way. And what's really at stake here is that the authors are raising the possibility to learn a lot about the Milky Way halo and its subhalo populations, and about using stellar streams to create a whole census of the dark matter subhalos in the Milky Way halo. And if we have that kind of census, that can give us really clear constraints on the population of dark matter subhalos, basically on the kinds of properties that we can expect for dark matter subhalos, right? And having such a census could in turn have really important implications for astrophysical dark matter, right? And so this is the third target that stellar streams are used to constrain. That's astrophysical dark matter. It's the boundaries to the space of possibilities for fundamental dark matter, right? Because if we learn more about how dark matter behaves on subgalactic scales, that could help us make progress on things like the small scale challenges. And it would help us also further enrich the astrophysical dark matter concept, right? And that amounts to building up tighter constraints on the space of possibilities for fundamental dark matter candidates. And so in the current case, it turns out that not all fundamental dark matter candidates would lead to the same amount of substructure in the Milky Way halo. And so if we're able to constrain the halo substructure, we can also constrain our astrophysical dark matter concept better. We can add in more sort of requirements for what a fundamental dark matter candidate would have to qualify. And so this is the third target that is investigated with the same stellar streams observations, namely astrophysical dark matter. And so here's a quote that sort of highlights that stellar stream research can be used to constrain the space of possibilities for fundamental dark matter. This is from a different research paper on GD1, where the scientists write, the evidence for the CDM substructure that's obtained can be used to constrain any particle dark matter that leads to a substantial suppression of the dark matter subhalo mass function on subdwarf scales, right? Okay. So that's the overview of the stellar stream case and of the different targets that are being investigated with it. And so in the reconstruction, I've once again tried to show that this detection of astrophysical dark matter with stellar streams depends on local eliminative inferences. But I've also tried to show that stellar streams are used to constrain 3 different targets. And so this is what I sort of mean by stellar stream research being multi-purpose, but let me say something more about this idea of multi-purpose research. Right? So ultimately, scientists are trying to get a handle on the behavior of dark matter on smaller scales, on subgalactic scales. One way they can do that is by mapping out the population of dark matter subhalos in the halo of the Milky Way. But that mapping exercise is only possible insofar as scientists can actually accurately map out the substructures in stellar streams and the impact scenarios that give rise to the stellar stream substructure, right? So what we get is that the research into astrophysical dark matter crucially depends on the success of the stellar stream research itself. Because if they don't even get the morphology of the stellar streams right, then the identification of dark matter subhalos and thereby the identification of good constraints on astrophysical dark matter, that will fail, right? And so in a sense, what that means is that the stellar stream reconstruction provides the background assumptions that are necessary for researching the dark subhalo populations. Now, in and of itself, right, the fact that experiments and observations depend on theory and on significant background knowledge, that should not be surprising. That point is sort of as old as analytic philosophy of science. We need a good theory of our detector in order to be able to use the detector to investigate a new target system, right? And so astrophysicists need a detailed model of their detector and the kinds of signals it produces, which in this case, the stellar stream is the detector. That's what Bonac et al. Called it. And so they have to understand their detector, their stellar streams really well in order to be able to use it for research in dark matter subhalos. But what I think makes this case sort of interesting, right, and revealing is that it's the same collection of observations that is serving these multiple purposes. It's used both to construct a model of the detector and to construct a model of the target, namely astrophysical dark matter, right? So detailed observations of the stellar stream substructure both serve to investigate how the stellar stream substructure can arise and to then trace out the substructure in the Milky Way or the subhalos in the Milky Way. And that subhalo population then constrains the space of possibilities for dark matter. And it's by heavily relying on this background knowledge that Abelson refers to in her account of local eliminative reasoning, the same set of observations is helping develop the theory of stellar streams, the detectors, and it serves to also, that same set of observations also serves to identify new phenomena, like constraining the dark matter subhalo population. And so that's what I mean when I say that this research is multi-purpose. It's the same set of observations that is doing all of this different kind of work. And that means that, in addition, right, that means that making progress on astrophysical dark matter requires making progress on a whole host of targets, right? In order to use stellar streams to constrain astrophysical dark matter, you have to understand stellar streams, giant molecular clouds, primordial black holes, Milky Way satellites, galaxies, and globular clusters, and so on, right? There's so much background knowledge that goes into play. But that also means that astrophysical dark matter research can actually allow us to make progress on a lot more problems than the dark matter problem alone. And so the success conditions for astrophysical dark matter research should be understood to be much broader than just finding astrophysical dark matter. Let me put it this way. Even if the scientists hadn't found a halo in GD1, oh, sorry, did someone?
We stopped seeing you and we cannot hear you.
Oh.
Okay, now I guess we can hear you, but we
Wait,
don't
is it back?
see you. The audio is back.
Okay, why did my video? There we go.
Now you're back.
Oh, okay. Sorry about that. I just suddenly got a notification of like something went wrong. But we're back.
Yes, we are back, but video, audio, as well as the slides.
Okay, perfect. Thank you. Okay, so let me put it, so what I was pointing at, right, is that making progress on astrophysical dark matter requires making progress on a whole bunch of other problems in the background as well. And that means that I think we have to rethink the success conditions for astrophysical dark matter research. And they're much broader than just finding astrophysical dark matter. Let me put it this way. Suppose that the scientists weren't able to identify a dark subhalo. Suppose that they're like, okay, we looked at GD1, we tried to find dark subhalos, but it turns out it was one of the luminous satellites of the Milky Way. That would still have been a success because they would have probably made a lot of progress about stellar streams and about the luminous satellites of the Milky Way and so on, right? So even if scientists weren't able to identify a dark subhalo, they would have learned so much more still about a bunch of other systems anyway. And so this was really the second claim that I wanted to establish, that astrophysical dark matter research tends to be multi-purpose, which means it contributes to progress on way more than the dark matter problem alone. And so far, I've been very optimistic about astrophysical dark matter research, but I have to admit that there are some clouds on the horizon, some important claims to reckon with. And that's one I want to discuss in this final substantive part of the talk, like in this final 5 to 10 minutes or so. A first issue that I want to highlight is on the scientific side, and that is that the identification of individual dark subhalos depends crucially, like using stellar streams, depends crucially on the adequacy of the local eliminative reasoning. And it turns out that setting up that local eliminative reasoning comes with serious challenges, right? There's more room for error, so to speak. Here's a paper by a different research group that re-examines the GD1 stream. And there's a couple of points where they disagree with the paper by Baerdemaeker et al. First of all, they disagree on the morphology of GD1. So they reconstruct what GD1 looks like in a different way. They actually don't think that the spur is associated with the gap that Baerdemaeker et al. Did. In addition, and how is this possible, you might ask? Well, it turns out that identifying member stars of a stellar stream and separating out from background stars and from Milky Way stars is really hard. That's one reason. Now, since they reconstruct the morphology of GD1 differently, they actually also think that the spur feature of the GD1 stream can be explained by an encounter with one of the luminous satellites of the Milky Way. So it's not a dark subhalo, they claim. It could have been a luminous halo. And so this paper shows that the constraints on identifying and constraining dark matter subhalos really depends on the success of the research in the stellar streams in the first place, right? In addition, I just want to mention that morphology of GD1 isn't the only point of contention. Some scientists use an entirely different method to do stellar stream research to investigate the dark subhalo population of the Milky Way. But for the reasons of time, I might not just go through this. Instead, what I do want to stress is that there are, I think, some more general challenges that I want to introduce and then gesture at a reply. A first challenge one might be concerned with is that the success of local eliminative reasoning relies on the availability of sufficient empirical data, and that we don't have that data in cosmology and astrophysics, right? So this is this idea that there's a sparseness of data concern because we can't run experiments or something like that in cosmology and astrophysics. Melissa Jacquard has sort of argued against the sparseness of data issues and has shown that there's various ways that scientists can get around them, and I think she's basically right. So I'm not too concerned about the sparseness of data concern. A second general concern that you might have, which is raised by Chris Meek and Sarah Gallagher, is the problem of uncomputed alternatives. And this refers to the fact that scientists can't always simulate all possible scenarios that they're interested in due to computational costs. But if scientists can't simulate all scenarios that they're interested in, that may introduce unwarranted selection effects or biases in their research. And in fact, this is something that Bonacca et al. Also recognize in their paper. They want to create a fully self-gravitating model of the stellar stream, but they don't have the computational power for it. And this is, I think, slightly more concerning, though I suspect it's something that can be actively kept track of. And so it doesn't necessarily imply that astrophysical dark matter research is doomed or something like that. Finally, is the concern that most of our knowledge of the structure of a galactic halo, and especially of a substructure in a galactic halo, comes from our observations of the Milky Way. But the Milky Way is only one galaxy, right? And there are many, many, many galaxies in the Milky Way, or in the universe. And so there's an open question whether the Milky Way is in fact a typical galaxy or not. This is something that scientists are actively researching right now. And so I just want to flag that if we want to draw general conclusions about the dark subhalo population based purely on our observations of the Milky Way, we better make sure that our evidential basis, namely our observations of the Milky Way, are representative of galaxies in the universe in general, right? So getting the typicality of the data of the Milky Way right is most important for the stellar stream research. And so I think this is a genuine challenge, but I also, and I'm not saying that the Milky Way is atypical or typical. I'm not saying anything specific in that context. In part because I have to learn a lot more.
Siska, we lost your video. I don't know whether we lost your audio as well. Let's wait for a minute or so, and meanwhile, Andres is going to write an email to her because I guess what happened is that her battery died, and she was trying to plug it when it died. So let's wait for a minute or so.
Am I back? Sorry, I just suddenly got like thrown out.
Yeah, don't worry. Just start sharing your screen. And this is a reminder to the people that are watching on YouTube. You can type your questions when the Q&A arrives. You can type them in the live chat box, and we are going to read them. If there is any question, we are going to read it here. Also, people in Zoom, you are going to be able to ask your own questions. So, Siska, please.
Yeah, I'm so sorry for these technical. Like normally, I don't have this many issues. I'm sorry. But anyway. So I was describing, if I remember correctly, I was describing this question of whether the Milky Way data is actually typical and a representative for like what dark matter halos look like more generally, right? and this is like an open question, but actually so this is a genuine sort of difficulty that the stellar stream research faces. But I actually also think that it fits well with this idea of local eliminative reasoning that I have adopted from Abelson. Because ultimately, right, establishing the typicality of the Milky Way data basically amounts to the fact that we need to fill up this gap in our background knowledge before we can proceed on the astrophysical dark matter research, right? This is like, it points us towards where our background knowledge needs to be enriched. So let me finally conclude. In this talk, I've tried to argue for three things, so here they are again, right? First, astrophysical dark matter research essentially relies on so-called local eliminative reasoning, an idea I've adopted from Abelson. Second, that astrophysical dark matter research tends to be multi-purpose, so constraining multiple targets at once, which implies that it can actually contribute to progress on more than the dark matter problem alone. And that also means, third, that the success conditions of astrophysical dark matter research are broader than usually recognized. Astrophysical dark matter research can be successful even if we haven't found evidence for astrophysical dark matter, I think. But I did highlight that there are some important limitations or concerns that scientists might have to reckon with. Thank you. Again, my apologies for all the technical difficulties. And here are some references.
Perfect. Thank you, Siska. And thank you, everybody. Let's thank our speaker with a round of applauses, reactions, and the applauses, or whatever you want to use. And now let's move to the Q&A. So, Siska, maybe you want to stop sharing your screen, and then we can get a huge close-up to you and to people who are going to ask. So, Andres first, Maximiliano, and Esteban. I'm going to type the list in the chat anyway, but please, Andres.
Hi, Siska. Thank you very much for your talk. So I'm struggling to see how this reasoning is, how the reasoning in dark matter research is at a global scale different from eliminative reasoning point. Yeah, eliminative reasoning without anything special. I would agree that in developing the alternatives of fundamental dark matter, local reasoning is a function. For example, there is a discussion of whether scalar field dark matter would include self-interactions or not, or whether it would include temperature or not, etc. But it seems that at a global scale, in the alternatives of dark matter, the map that you showed, local reasoning falls short. That's my concerning, because the alternative seems to be complex enough to be more than models of the CDM part. And if one adopts, for example, primordial black holes or WIMPs or this scalar field dark matter, there seems to be broad inferences that can be obtained regarding the history of the universe. So what would you say on this?
So let me clarify. If I understand you correctly, right, what you're saying is when we actually look at all of the possible candidate fundamental dark matter concepts, right, like WIMPs, primordial black holes, all of that, that can't rely on eliminative reasoning.
Yeah, I'm concerned that to reject those models, to propose them, are simple modeling decisions. The core concept of the dark matter seems to be thin enough for one to simply decide what to model or not. It seems to me that local eliminative reasoning is better adapted to what to move in particular candidates, but not at that global scale of dark matter candidates. Yes.
I see. So, okay. Good. I disagree. So let me lay out sort of how I think about this, right? And so let's see if that answers your question, because I'm curious about whether I clarify it. So I started out with this distinction between astrophysical and fundamental dark matter, right? And this astrophysical, that's like the thin common core concept. It's more or less what Niels Martens refers to as like a thin common core concept. If, I don't know, you know about that. You seem to know about that paper. Good. Good. Yeah, I thought so based on your time. Anyway. So that's like this thin common core concept. And it's the set of properties that all fundamental dark matter candidates have in common, right? What I'm trying to say is that there is a set of research ongoing right now that isn't interested in figuring out whether dark matter is constituted by WIMPs or primordial black holes, or that's not primarily aimed at figuring out which one of the many, or axions, right? Which one of the many candidates constitutes dark matter. But what it's interested in is figuring out, are there other properties that we think dark matter needs to have in order to fulfill its role in cosmological structure formation and in explaining like galaxy dynamics, cluster dynamics, and so on, right? And the area where that primarily happens, I think, is on galactic and subgalactic scales, because that's where there's all of these open questions, these small scale challenges, right? And so what I'm trying to say is that if the goal of the research is to try to figure out what dark matter generally, no matter what it's constituted by, right? What kinds of properties it needs to have to play its particular role in cosmology and astrophysics, that kind of work has to rely on local eliminative reasoning. And the reason it has to is because we have limited empirical access to dark matter. Because right now, all we know is how to detect it through its gravitational effects. I'm not saying that's like epistemically bad or something like that. I'm just saying what that means is that in order to figure out if we actually have empirically detected it or if we're encountering some other kind of effect, we have to do this kind of local eliminative reasoning, right? And I think, in fact, I think the opposite is the case when it comes to these fundamental dark matter candidates, right? When it comes to like WIMPs or axions and so on, because I think there, suppose that we find positive evidence that a WIMP has been detected or something like that, right? I think it is still then an open question whether that one particle candidate that we've detected is responsible for the entire dark matter budget of the universe, right? And so I think there, just that you can't, like, there needs to be more work that has to happen, I guess, in that context. Does that answer the question a little bit? Okay, let me know if, I'm happy to talk more, but yeah.
Thank you, Siska. Thank you, Andres. Maybe we can go back to Andres in the end of the list. So I think Maximiliano, please.
Yeah. Thank you for the talk, Siska. Sorry, my English is very poor. My question is, how do you connect the studies or investigations or the multiple purposes that investigate the or characterization of dark matter, astrophysical dark matter in the local universe, with the studies or investigations they are about the big scale universe? I mean, think a strategy of the local galaxies are the building blocks of the universe, a big scale, or in a way around. What do you think about that?
Yeah, good. This is, well, solving that question would be a big, sorry, let me say it slightly differently. Ultimately, what the small scale challenges amount to, right? These discrepancies between what we derive from lambda CDM and what is observed for galaxy scales, that's ultimately about that question, right? Because lambda CDM describes the evolution of the universe at the largest scale. So that's like, you know, bigger than clusters, basically, right? It's like the large scale structure of the universe. And then The small scale challenges are like, okay, we start with that model and then we try to zoom in to smaller and smaller scales. But the issue that of course then gets encountered is that on large scales, gravity is dominant. On smaller scales, a lot of non-gravity becomes relevant, right? A lot of what they call gastrophysics and so on become relevant. And how to model that is super complex and not necessarily, I mean, this is like a work in progress in science. So there's genuinely an open question. At the same time, we do know from our theories of structure formation that likely, galaxies form in halos, right? And so we do know that like the dark matter on the largest scale is also what's relevant on galaxy scales. We do know that it's like the same thing that's supposed to function on all of these different scales. On that, we have like on the fact that it's the same stuff, I think is very well established scientifically. The question is figuring out the details of how you get to the smaller scales. Yeah.
Thank you. Nice.
Thank you very much. Now let's move to Esteban and then Sergio, please.
Hi, thank you for your talk. I have a question about how restrictive could the astrophysical side of research end up being if we focus too much on the local eliminative method, because it appears as well, according to what you presented, that there's a lot of focus on empirical challenges, data evidence, computational challenges, and so on. But the diagram you showed at the beginning, considering the different possibilities that people on the fundamental research side want to explore, are also theoretical in character. So that would be my question. If the local eliminative method, wouldn't it be too restrictive? I mean, assuming in the background knowledge the only the theoretically already accepted and standard knowledge, instead of opening more theoretical possibilities. Thank you.
Good. Thanks. So if I understand your question correctly, right, your concern is like doing this astrophysical dark matter research, given the amount of background knowledge that we already have to rely on, it's not really going to get us far enough to answer all of the open questions that there are perhaps about dark matter and about its fundamental nature.
No.
Okay,
No,
sorry. Then please,
just focusing on the local eliminative strategy. So from the start, it looks okay that astrophysical dark matter research gives you the possibility space for research in fundamental dark matter. But it seems I'm just trying to understand it better. So it seems that the local eliminative strategy by Abelson restricts the space too much on the side of evidence and data and computational challenges and so on, and leaves perhaps little space for more theoretical research so related to astrophysical.
I see. Okay.
Research as well.
So your concern is that this idea of local eliminative reasoning, because it's always focusing on cohering with the background knowledge, there's not much room for like broad speculation.
It's a question. Yeah, it's
but is that the question?
Yeah.
Okay, good.
Something
I just
like
want to
that.
make sure that I got it, that I understood it well. Thank you. Thanks for clarifying. Good. So I think that concern I don't share it. I don't think this concern is really applicable in this context, or that this is something that we should be too worried about. Because the idea behind local eliminative reasoning, yeah, it does require that you rely on a bunch of established background knowledge. But that background knowledge is usually very well established on different grounds, right? Like the way we know about the Milky Way disk and the Milky Way density, like the density of the Milky Way disk, for instance, right? That's based on a whole bunch of available empirical evidence that is just part of our background knowledge and that we want to be consistent with, right? And that we want our models to be coherent with, right? And I think the same goes for most of this like background knowledge that we rely on in these eliminative inferences. The reason that they're considered background knowledge is that we believe that we have significant supporting evidence for it, and for the theories that these models rely on, and so on, right? And so I think this concern about, or like, I don't think that necessarily means that like we're missing out on like hugely hugely innovative theories because we're focused too much on what coheres with our background knowledge. Because ultimately, in order for these hugely innovative theories, say, to be accurate, right, or to be well supported, it would mean that we would have to probably overturn most of our knowledge of modern physics, right? Because most of astrophysics and cosmology, at least the sort of well-established parts of it, are based on very well-established ideas about physics, right, that we would want any future theory to recover anyway. So I think that's why in these like local contexts where we're focused on trying to detect astrophysical dark matter, we can really rely on this broad background knowledge. And it's the only way to sort of make progress. But thank you for your question. It's interesting to think
Thank
about.
you.
Thank you, Esteban and Siska. Now, Sergio, please.
Yeah, thank you. Thank you, Siska, for the keynote. I have two questions. The first one is if you could share the title of the article for local eliminative reasoning, the Ivelson article. Could you? But my question is if
Siska,
you could.
I have it open on my computer. Do you want?
It's called,
Oh,
so
great.
I'm sharing the references, I think, right now. So you should be able to see it, right? It's Abelson 2025 in philosophy of physics. It's called Eliminative Reasoning in Astronomy and Astrophysics.
Yes, thank you very much.
You're welcome. It's great. I think it's a great paper.
I got very excited about the article. So yeah. And my second question is about the eliminative reasoning. Could it be applied or extended to cosmological research in a broader scale? And this, I think this question has to do with what Maximiliano was asking too. So I ask it because of this. You said that for dark matter, we only have access, we only have gravitational access, right? So I have this concern about how we measure or how we date this universe history, this universe evolution or age even. So I mean, for history we have all these documents, right? So we can go and research about the documents about the people that lived the events, right? But in the case of the origins of the universe, we do not have any access of that sort, right? So my question is that if this eliminated reason could be extended, right? So for the research about the history of the universe, the age of the universe, or is it applied somehow? Thank you.
Thanks. So it ties back to what I said about the paper being great before. So actually, Abelson, in her paper, she proposes that this idea of local eliminative reasoning is basically the epistemology that applies to astronomy and astrophysics more broadly. And she gives 3 different examples in her paper. And so basically what you can see, what I've been doing is like giving a 4th and a 5th example of this kind of local eliminative reasoning in astronomy and astrophysics. So it definitely applies much broader than just the astrophysical dark matter research that I've been discussing, but my focus is on that for separate reasons, right? And so I think it's an interesting question as to how it applies to cosmology. I think for certain branches of cosmology, it seems very plausible to me. But there's areas of like early universe cosmology where I would have to think about it. Let me put it like, I'm not going to give you a yes or a no, but it's definitely not it's definitely not implausible to me. Yeah.
Thank you very much.
Thank you, Siska. And now there is a question from Facebook. I'm going to read it, but it's also posted in the chat by Andres. You argue that astrophysical dark matter research relies on eliminative reasoning that is local and model dependent, and that the same observations constrain multiple targets at once. How do you think this should affect how we assess evidential support for dark matter itself, as opposed to support for broader modeling frameworks or auxiliary assumptions?
Good. This is an interesting question. I think, in fact, what I definitely don't think we should conclude from this is that it somehow means that our evidential support for dark matter is weaker or something like that, because it relies on a lot more background knowledge. In a sense, I think in many ways, the way evidential support happens in science, it always relies on a lot of background knowledge, right? And so I think when it comes to the case of dark matter, a lot of the evidence, like the individual lines of evidence in support for dark matter, each rely on a lot of background knowledge. At the same time, there is such a wide range of evidence that we have for it at this point, where there's where I think you can sort of run a kind of robustness argument or a variety of evidence argument in support of the existence of dark matter. So like I don't think that it like mitigates the strength of our evidential basis or like our empirical support for the existence of dark matter or anything like that.
Thank you very much.
It just situates it. Sorry?
No, thank you. Thank you very much. So there's a last question. I will ask you to stop sharing your screen.
Yeah.
And then Charlie, please.
Hello, thank you, Siska, for your talk. I really like this idea of local eliminative reasoning. And I wanted to ask one question about it. Like, you said that it seems very difficult to set it up, right? That in this context, sometimes they may fail or disagree between different studies. I just wanted to ask your opinion or intuition about, do you think in the context of astrophysics, in dark matter, do they manage to overcome those difficulties? And so is it for you a fruitful methods, or is there more difficulties and they maybe should go another way? Like,
do you mean, sorry, when you say like, what's my intuition, do you mean about using local eliminative reasoning or about using these stellar streams?
Using local eliminative reasoning.
I see. Good. So yeah, so let me once again reiterate that this paper by Abelson, from which I've drawn this idea, is excellent, and I highly recommend you all read it. But this idea of, and I love that Andres is like posting so many references to great papers in the chat. The paper by McCoy is also great. And I think there's a paper on the paper by Rosa. Anyway, yes, I recognize these papers. They're great. Read them. Anyway, sorry. Back to your question, Charlie. So do I think that they should go another way? So no, because I mean, science is hard and it's not going to be difficult in the context of dark matter, right? And in fact, there's difficulties to setting, there's going to be disagreements more often in science about methodologies, about how to interpret evidence, things like that. If anything, I think this kind of local eliminative reasoning that Abelson describes so clearly, I think if anything, what that framework helps us to do is to identify the specific location where people disagree, right? Because in this case, it's already at the starting point. Like, what are the observations that we're even trying to explain? Like, that's already a point where people disagree. And that like gives you also a fruitful way of moving forward, right? It's like, okay, how do we resolve this particular point of disagreement? So, you know, in a sense, there's a way in which you can flip it around where it's like every time you run into a difficulty or a point of disagreement, that highlights, okay, well, where should I focus my research efforts? And so yeah. And I think the epistemic situation in dark matter research is what it is, with that we only have gravitational access to it. And so I'm not sure that there are that many alternatives possible to this idea of local eliminative reasoning anyway. So, yeah.
Super, thank you.
Thanks.
Thank you very much. If there are no more questions, neither on YouTube nor here, there are no more questions on YouTube, and there are no more people raising their hands. So let's thank Siska for this super interesting talk. And thank you, Siska. It was a pleasure to listen to you.
Thank you for having me. Sorry for all the technical difficulties.
No, don't worry. I think it went really smooth in general. So there was no actual rupture between what you were saying before and now, so that's fine.
Okay.
Now let's move to the first contributed talk of the day, which is going to be by Andres Vasquez. It's worth mentioning that Andres has carried the duty of organizing this event mostly by himself, with the help, of course, of Ana Rosa Perez Sanz and Luis Estrada. So Andres, welcome to your own workshop, and please try to share your screen.
Yeah, thank you.
We are going to start this one a little bit earlier, 5 minutes earlier, but I think that's going to be absolutely fine with people on YouTube and here. So,
Almost there. Yeah.
well, Andres is a student from the graduate program in Philosophy of Science at UNAM. And Andres, the floor is yours. You have 30 minutes for presentation, and then we move to the Q&A.
Well, thank you. Hello, everyone. I hope you're doing very well. I hope you're enjoying this great event also. Today, I'm going to be tackling the question of whether ad hoc modified research programs are worthless of pursuit, or rather they can be rationally pursued. Right, so let me briefly explain the title. So what I'm going to address here is the effect of ad hoc modifications on the epistemic reliability of research programs. Right, so I take epistemic reliability to be a graded property of that is related to the attitude of scientists towards a theory or research program. A high epistemic reliability should be consistent with the acceptance of the program, and a low epistemic reliability should be consistent with the rejection of such program. So, as Loudon has explained, there is a panoply of attitudes between acceptance and rejection. Pursuit is one of them. Right, so the skeleton of the argument is this. Traditionally, ad hoc modifications are below the pursuit level, on the rejection level, right? Charges against the dark matter research program tend to have this form, as it was ad hoc introduced and ad hoc modified towards its development. It should be better be rejected. And also, these kinds of charges argue that we should take a less ad hoc alternative like the modified gravity research program. However, similar charges can also be pointed to this program. I leave the references here if you want to check them out. But this is not the only problem. In fact, future development on both research programs may require further ad hoc modifications to such programs. Moreover, The significance of ad hoc judgments is dubious as there is no adequate account of ad hocness. What I want to say here is that there is no current definition of ad hoc that generally identifies historical cases of ad hoc hypotheses and also give a proper analysis of ad hoc. So what is needed is clear. We need a novel way to identify ad hocness, which also allows for rational pursuit under strict epistemic conditions, right? So the argumentative strategy of this talk is the following. First, I will stress the epistemic status of ad hoc hypotheses on traditional accounts. Here, I will show that we currently have no alternative that can at the same time identify historical cases and also provide a proper analysis of ad hocness. Then I will argue that in spite of not having a good definition, we can still associate an epistemic signal to the introduction of ad hoc hypotheses in terms of epistemic risks and some forms of ignorance. Finally, I will use this epistemic signal to claim that ad hoc charges to the dark matter research program are legitimate, but that doesn't mean that it is to be rejected. There are certain risk management strategies that have been followed in order that they provide certain theoretical virtues that make the epistemic reliability consistent with rational pursuit, right? So let us begin with the common accepted definition of ad hocness. So, at least in a colloquial sense, ad hoc means formulated for a specific purpose. In science, this typically means that we need to restore the agreement between data and theory. That is the specific purpose ad hoc hypotheses are frequently recurred, right? So schematically, what happens is this: you have a unique and unexpected empirical result, an anomaly, that is an anomaly regarded to a certain theory, but not to the theory plus the ad hoc hypothesis, right? Again, traditionally, these modifications are associated with a decrease in the epistemic reliability of either the theory or the research program whole. However, this is a contradictory conclusion because we have, if we look at the history of physics, we have cases of successful ad hoc hypotheses and also failed ad hoc hypotheses. An example of a successful ad hoc is Planck's quantization of energy. It was introduced to save an anomaly. However, to pursue it was rational because ultimately it redefined our understanding of reality, right, with quantum mechanics. An example of a failed hypothesis is Lorentz featural contraction, which is just to save the luminiferous ether theory, right? So accounts of ad hoc hypotheses tend to have these two historical cases as a benchmark for their adequacy, right? If they are good enough, they will regard the Planck's quantization of energy as temporarily ad hoc and the Lorentz Fitzgerald contraction as generally ad hoc. So what are the technical accounts of ad hoc hypotheses? Well, the first is independent testability. Ad hoc hypotheses are those that cannot be independently tested. And the epistemic risk that these authors point to is circularity. So what they explain is this: if the anomaly supports the modified theory and the modified theory explains the anomaly, then there is some sense of circularity, right? In this view, Planck's hypothesis ceased to be ad hoc because it had independent tests. For example, the photoelectric effect. But the Lorentz Fitzgerald contraction hypothesis, as it lacked independent tests, it remained ad hoc forever. However, there's a problem with this, and to begin with, there is no risk of circularity. It would be circular if the anomaly explained the modified theory and the modified theory explained the anomaly, but this is not the case. To be evidence of and to explain something are different functions. Yeah, so there is no risk of circularity. And in fact, the Lorentz-Fitzgerald contraction actually had independent test. That is the Kennedy-Thorndike experiment, which actually falsified it. So that was the first account. The second account is lack of unifiedness. Ad hoc hypotheses are those that are provided to a theory which faces a panoply of anomalies. So, and the risk is that if you are already suspecting a theory of not having the theoretical resources to give a unified account of their anomalies, then why would you try to save it from refutation? Yeah, in this account, Planck's hypothesis as well as the Lorentz-Fitzgerald hypothesis seem ad hoc, right? But however, there is a problem because this notion of ad hocness doesn't allow for local ad hoc and global ad hoc. It only seems to admit global ad hoc. And there seems to be a sense in which we need the concept to capture the case where there is a single anomaly and an ad hoc hypothesis is provided to save the theory from refutation, right? So it doesn't give proper analysis on what ad hoc is. Finally, we have the coherence strategy. So in this view, ad hoc hypotheses are those that do not cohere either with the original theory nor with the theoretical background. And what does it mean to cohere? Well, according to Schindler, cohere is to have good support. If an hypothesis lacks good support stemming either from the theory or from the theoretical background, then it is ad hoc. Planck's hypothesis ceased to be ad hoc because in spite of at the beginning having no support, when statistical physics and quantum physics developed, it had, of course, good support. The Lorentz-Fitzgerald contraction never had good support, and thus it was always ad hoc. So the problem is that Schindler argues that coherence is an objective property of hypotheses. The question of whether a hypothesis coheres or not should be objectively answered. But the notion of good support is rather ambiguous, and thus it doesn't matter much if it is objective or not if scientists cannot agree on what is coherent, on what is good support, right? So it does, although it signals well historical cases, it doesn't provide a good analysis on what ad hoc is. So how can we safely identify ad hoc modifications, and what is the epistemic risk developing ad hoc modified theories? Because if these accounts cannot provide a good analysis on what ad hoc is, their explanations of the epistemic risk also do not follow, right? Well, whether we find a definition, an adequate definition of ad hoc hypotheses or not, we can still identify their epistemic signal by looking at the epistemic risks and the ignorance, right? So let us take Schindler's account instrumentally. If you lack good support for a hypothesis, that also means that you don't know if it is true or false. And thus holding such hypotheses leads to taking an alethic risk, a risk of holding a false belief. But also, if you lack good support to a hypothesis, then the hypothesis itself could not is suspect of not providing proper understanding of the anomaly, right? Of not grasping the underlying causal structure. So, in holding such ad hoc hypotheses, one runs a shallowness risk, the risk of having a shallow account of the anomaly. And if we take these two and aim it not to the hypothesis, but rather to the theory, we get crisis risk. Imagine that the ad hoc hypothesis is actually true, and it actually gives some not shallow account of, but rather reveals that certain central parts of the theory are flawed. Then it would lead the theory to a partial state of crisis. And to avoid crisis, one would decide to take the tenacity's method of Peirce, right? And for example, decide not to take any anomaly at all. But if we decide to that, we then take Pyrrhonic risk. That is the risk of not forming any beliefs at all. And that is comparatively worse to holding some false beliefs and some shallow accounts. So now, these risks have an interplay. We cannot minimize them all, but we are relegated to just regulate these risks. For example, we can regulate the Pyrrhonic risk with dialectic, shallowness, and crisis risks. If we lower the Pyrrhonic risk, then we have to take some amount of alethic, shallowness, and crisis risk. Yeah, but that is the price of research, right? Now, in order to regulate crisis risk, we have to also regulate alethic and shallowness risk. Moreover, in order for science not to become in somewhat truth fetishism, as Pritchard mentions, we need to have not only true beliefs, but also to have a grip on truth. That is, to understand how these true beliefs hold together. And thus, we might accept a certain structure between these beliefs, but we then take the risk that this structure may not be good enough, that it may lead us to hold some false beliefs, but even that is desirable to not having any structure at all, right? Now, there is a subtle distinction between taking a risk and causing conscious epistemic harm, and that is ignorance. Yeah, if one ignores the certain outcome of a situation, then one takes a risk. But if one knows the certain outcome of a situation and still takes it, then one falls into conscious epistemic harm. That distinction is mediated then by ignorance. So let us briefly review ignorance. So there is factual, objectual, and ignorance of theoretical structure. Yeah, ignorance is just lack of knowledge. So if we ignore facts, that means, for example, that we lack knowledge regarding the truth values of some propositions. And that explains alethic risk. Yeah, because we ignore certain truth values, we take some alethic risk. Objectual ignorance, is ignorance regarding the full relevant properties of a certain object. In fact, not only the relevant, but the identity properties of the object. This partially explains shallowness risk, because in having a shallow account of the causal structure, it may be that we lack a certain property, which taken together would render our understanding as proper, right? But there is a more fundamental ignorance, and that is ignorance of theoretical structure, which subsumes factual as well as objectual ignorance. And this form of ignorance is ignorance of the relevant propositions or the inference patterns science typically allow for. That is, empirically adequate inference patterns or valid inference patterns, and so on and so forth. Right, and so if this ignorance subsumes the other two, then it also indirectly explains alethic and shallowness risk, and also crisis risk. right? So right now, we could barely say that ad hoc hypotheses are those where there is ignorance of theoretical structure that causes certain epistemic risks. Yeah, but we have to account for successful ad hoc and for failed ad hoc hypotheses. So what will be the difference? What's going to be the difference? Well, we're going to rely on the distinction that we have traced about taking a risk and causing conscious epistemic self-harm, conscious self-epistemic harm. Yeah, right. So Grunbaum argues that if we look at the history of science, at the history of physics, for example, there is a motivation to distinguish between descriptively ad hoc and pejoratively ad hoc. The first would be such hypotheses whose current relations with the with the available scientific resources at a certain time are weak. Pejoratively ad hoc would be those hypotheses where the relations with the available resources are hardly repairable. And that's how he saves the Planck's quantization of energy and the Lorentz featural contraction. The first is a case of descriptively ad hoc hypothesis, and the second of the pejoratively. Now, what if we define descriptive ad hoc with unresolved ignorance, and thus that the epistemic harm has not been manifested, and pejorative ad hoc with resolved ignorance, and that the epistemic harm has been manifested? Well, then we have not only an a posteriori account of why we need this distinction, but also some form of a priori reason. Why? Because when facing an anomaly, we can decide to suspend judgment, but that would be to take Pyrrhonic risk, right? We need certain descriptive ad hoc hypotheses in order to lower this Pyrrhonic risk and to restore the production of knowledge. So this is how we show that descriptive ad hocness is insufficient to warrant derogation as unreliable. Pejoratively ad hoc is a different story, right? That would certainly be sufficient to warrant derogation as unreliable. So these are my definition of the epistemic signal of descriptively ad hoc and pejoratively ad hoc. Note that both definitions have an anomaly component, and that's because even though the authors disagree on what ad hoc is, they almost all agree that ad hoc hypotheses are those that are provided to a theory which faces an anomaly. Yeah, so that's why it is there. But the difference between descriptive ad hoc and pejoratively ad hoc is ignorance. Descriptive ad hoc are those hypotheses which, taken together to the theory, decrease Pyrrhonic risk by increasing alethic, shallowness, and crisis risk. Pejoratively ad hoc are those that, together with the theory, certainly reduce Pyrrhonic risk, but do so at dramatically increasing alethic shallowness and crisis risks, because the manifestation of the epistemic harm when pursuing such modified theory has already resulted in epistemic harm. So I want to make clear that what I'm giving here is not a definition. A signal, is not a definition. I am not giving nor necessary nor sufficient conditions for ad hocness. What I'm giving here is strong evidence of having found an ad hoc hypothesis. For example, if we take Planck's hypothesis, the claim that such hypothesis cease to be descriptively ad hoc is supported. Why? Because it was certainly introduced in response to an anomaly, and it was certainly the theory plus this hypothesis was certainly pursued under conditions of ignorance of theoretical structure. No one knew how could the exchange of energy would be in a discretized manner, right? But after statistical and quantum physics developed, such ignorance of theoretical structure was resolved, and thus we do not longer have an descriptively ad hoc hypothesis. Meanwhile, the claim that the Lorentz feature contraction hypothesis is pejoratively ad hoc is also supported. It was a response to an anomaly, but also past attempts to pursue it have resulted in the manifestation of alethic and shallowness risks. As I mentioned, the Kennedy-Thorndike experiment tried to test this idea of the Lorentz contraction and failed. Now that we have this epistemic signal, we can answer the question of whether the dark matter research program has been modified ad hoc. Now, as Siska explained, textbooks report that 27% of the material content of the energetic content of the universe is composed of dark matter. That is matter that is invisible, non-baryonic, and cold. I mean, matter that does not interact with the electromagnetic field, that is not composed of protons, neutrons, etc., and whose receding velocity is much low compared to the speed of light. Okay? So, from the very beginning of the introduction of the hypothesis, it was ad hoc because it was introduced as a response to an anomaly, an anomalous missing dynamical mass. For example, we can see this in Zwicky's work, right? But crucially, the dark matter concept was not introduced by Zwicky, but by people that are named Captain, Jan Oort, and also Poincaré, who commented on Kelvin's research. Well, this first form of dark matter was not what we understand now that is dark matter. They thought that dark matter consisted of gas, dust, faint stars, and so on and so forth. This is in principle visible matter. Pursuing the theory plus the hypothesis was certainly done under ignorance of theoretical structure conditions. Because in spite of knowing what this dark matter could be and how it would interact with other forms of matter, they did not know a central premise, that is, in which I don't know how to say, in which proportions do we need gas, dust, and faint stars in order to account for the dark matter hypothesis. Of course, they knew what the sum would be. The sum, yes, but not what single component. And that is ignorance of theoretical structure that led ultimately to alethic, shallowness, and crisis risks. However, when scientists took this question seriously of whether there was dark matter or not, they found a problem. If they held that dark matter was composed of, in principle, visible matter, then this form of matter could not account for the total sum. In fact, they certainly found some gas, some faint stars, but not in the abundances that they needed for them to resolve the anomaly. So, in fact, including other measurements as microlensing, Big Bang nucleosynthesis, the abundances of chemical elements, and so on and so forth, an ad hoc modification was motivated, that dark matter was actually invisible and non-baryonic. It was also introduced when facing an anomaly, and also the context, although the context was comparatively less uncertain, it was pursued under conditions of ignorance of theoretical structure, because the candidate that they thought that would resolve the anomaly was the neutrino, and the physics of the neutrino were not well understood. Right? So we move on to the history, and we see that when they tried the neutrino as a serious candidate of dark matter, another anomaly was faced, and it was that this form of dark matter, which is dubbed as hot dark matter because its receding velocity is almost equal to the speed of light, it could not form large-scale structures just as we observe them today. If we take the neutrino to form all dark matter, then we should not see the universe that we actually see, right? There is an anti-hierarchical growth, right? So they changed from hot dark matter to cold dark matter. And that was introduced again when facing an anomaly. And again, although the context was less uncertain because scientists gathered many facts, this novel form of dark matter that is invisible, cold, etc., is pursued under ignorance of theoretical structure conditions because we have to posit more exotic particles such as the WIMPs, the scalar field dark matter, and so on and so forth. No, to the question, has dark matter introduced ad hoc modifications? Yes, it has the epistemic signal at least. So now, are there grounds to believe such pursuit has been rational? Well, also yes, because there are risk management strategies that, when followed successfully, they ultimately grant some theoretical virtues that make the empirical reliability of the research program compatible with that of rational pursuit. The first strategy that I present is cautionary development. And it captures the idea that in order to reduce the pruronic risk, we have to take some alethic and shallowness and crisis risks. This strategy addresses directly ignorance of theoretical structure because it requires scientists to devise empirical tests, conjugate different parts of theoretical background, trying, for example, for coherence, consistency, and reformulate basic tenets, etc. All the activities that scientists typically do. As I mentioned, if successfully applied, it can grant some theoretical virtues like coherence and unificatory power. Why? Because if we use the modified theory to interpret more observational data and this activity is successful, then we have certainly unificatory power, right? Unificatory power. This
Andres,
strategy, yes.
You have 5 more minutes.
Yes, I'm already ending. This strategy is well exemplified by Zwicky's contemporaries, as they gathered more data, developed the theory, tested for the virial theorem, for example, or the equilibrium conditions, etc. The second strategy is assessment and compartmentalization. Yeah. So this strategy locates ignorance of theoretical structure, as it requires scientists to assess the scope of epistemic risk and to strengthen the catalyst paribus conditions of the most successful but plausibly having to be modified parts of the theory. So what this strategy is doing is to regulate risk, preventing epistemic harm to propagate to the whole theory. An example of this is the assessment of the virial theorem and the equilibrium conditions, right? And the final strategy is this, distribution of risk. And this strategy demands to look for more and more varied kinds of empirical data, but also more alternatives to account for the anomaly. What this strategy is doing is distributing the available resources to give a robust resolution to the underlying ignorance of theoretical structure. It regulates alethic and shallowness risks in that some scientists concentrate on gathering facts, and other scientists concentrate on formulating new alternatives. Now, in order for the production of alternatives not to explode, one needs somewhat a limit. Yeah. And this limit is provided by the no alternatives argument, which is an idea posited by Richard Dawitt. If we want me to explain more how it works, just ask me at the end of the talk. Finally, if successfully applied, this distribution of risk strategy would grant robustness and fertility, which are also theoretical virtues that are consistent with rational pursuit. In fact, I also think that there is a sense in which eliminative reasoning has to do with the formulation of alternatives here, but not a local, but global. Yeah, one founded in McCoy's paper. Right, so let's go straight to the conclusions. Non-problematic form of ad hoc is currently available. They either fail to identify historical cases or to provide a proper analysis of ad hocness. And to account for successful and failed ad hoc hypotheses, we need to distinguish between descriptive and pejoratively ad hoc. And in spite of not having a good definition of ad hoc, we can still identify the epistemic signal of introducing an ad hoc hypothesis. And we can also assign a signal as a characteristic signal to descriptive and to pejorative in terms of ignorance, unresolved ignorance or solved ignorance. Finally, the dark matter research program has introduced modifications, ad hoc modifications, but the successful application of risk management strategies have led it to be the epistemic reliability consistent with rational pursuit. And well, that is all. Thank you.
Thank you very much, Andres. Now let's move to the Q&A. Yes, please thank the speaker with a round of applauses. Andres, I will ask you to stop sharing your screen so we can get a close-up of people interacting now. So let's move to the Q&A. People here, reactions button, raise your hand, and people on YouTube and on Facebook, just type your question in the chat. So Siska first.
Hi, thanks. This is cool. I have two separate questions, but let me just ask one first, and then if I have time later on, I can add myself back to the queue. The first question that I want to ask is like, you give this account of like the history of dark matter, and you say like, look, there were some ad hoc modifications that were introduced, but it was a rational reason for pursuit. I'm kind of wondering, maybe I missed this, but I'm wondering to what extent does the fact that from particle physics, we know that there's like likely a need for beyond the standard model physics, right? How does that feed into this these assessments of ad hocness or rationality of pursuit, if that makes sense? Like the fact that we know that like our standard model of particle physics is incomplete. How does that feed into the assessment of dark matter in context of this ad hocness and rationality of pursuit?
I have a question on that. Do you mean the sole fact of knowing that the standard model is incomplete, or particular candidates to fill that hole?
Well, let's say both, because now I'm curious why you think the difference is relevant.
Well, I think I mean, you could think that ad hoc hypotheses are those that lack good support, as Schindler does. What I'm thinking here is that defining ad hoc is somewhat difficult, right? Because there are many senses in which good support can be provided, and just lacking some particles in the standard model may not be sufficient reason to account for this dark matter, as this could be other forms, as you have also explained. We could have primordial black holes, scalar field dark matter, and so on and so forth. So I want to ask you, is your question, I mean, is for you, would it be the case that these missing particles would render the dark matter hypothesis as less ad hoc? Would it be the case for you?
Well, comparatively to, for instance, MOND, which you mentioned at the beginning, I would say yes. Because of the consistency with the theoretical background, with established theoretical background, right? Like part of why I think that dark matter was much less ad hoc, regardless of how I would have to think about which kind of ad hoc, but why it is maybe descriptively ad hoc and not pejoratively ad hoc is because there's different features that show that it is consistent with our theoretical background, if that makes sense.
Yeah, now I see clearly your question. And I think these strategies of looking at the extensions of the standard model fit into the look for alternatives strategy, right? And there you can use eliminative reasoning and all that you have said already. But I also think that exploring modified theories fit into that category because we're exploring the possibility space. In fact, what I'm claiming here is that if we take this epistemic signal as serious, then we could also render reassess the whole MOND dark matter debate in a more firm base. Because both programs are ad hoc. The question is, are they descriptively ad hoc? Do we have reasons to pursue them, or we do not? Am I explaining myself clearly? Yeah.
Thank you very much, Siska and Andres. Maximiliano wrote a comment on the chat. I'm just going to read it so for the audience in YouTube. Thank you, Andres. This talk reminds me of the underlying idea of the Zwickis morphological method, using strategies to get rid of epistemic prejudices and give a particular shape to an observational concrete problem. Do you want to say anything on this? Do you have any comment on?
Well, first I want to thank Maximiliano. I did not know about this morphological method idea. If you have any particular reference, I would very much like to read it. But yeah, I think that there is a sense in which the ad hoc judgment serves as somewhat aesthetic judgment that the solution does not seem right. What I'm looking for here is to give a more firm ground to account for ad hocness. That's all. Yes.
Perfect. Now, meanwhile, I have a question myself, and it relates to the detection of what type of ad hocness is happening in a particular context. Because my impression is that cosmological model extensions are often introduced in context of high uncertainty or high levels of underdetermination. And because of this, it might be very difficult to detect whether there are certain epistemic risks at play.
Sorry, your microphone is sounding weirdly. I don't know if you move. Yes.
Yeah.
Better now.
So my question is, cosmological model extensions are often introduced in contexts in which there are high degrees of underdetermination or high degrees of uncertainty, and this might make murky the environment to detect which type of ad hocness is at play. Because in your example, and I think it's very easy to go back in time and to make this detection, not only exactly in the case of dark matter, but in cosmology in general, it's very easy to make reconstructions of how the debates evolved in the past. But maybe it's not so easy to see which type of risks people are facing at a particular moment. And especially because you depend on a notion of ignorance that is very much deepened as lack of understanding of what are the theoretical commitments. And so that only increases the degree of uncertainty. In general, my fear is that this detection can only be made a posteriori. Do you have any intuitions on that?
I mean, is your concern that maybe this epistemic signal is signaling all cosmology?
Not necessarily. That the way in which we interpret the epistemic signaling might not be so as neat as you presented it. It can be very clear to us when we look in retrospective for past cases, but in present cases, people might be working with something trying to fix holes, and we call it ad hoc, but whether it's like of the good ad hocness or bad ad hocness, that we don't know yet. And it's very hard to know. So I was wondering whether you agree on this, or you have some intuitions on what can make it more clear for the detection of the type of ad hocness in modifications in cosmology.
Yeah, so I now understand your question very clearly. What I think is that, in fact, yes, sometimes you take more risk, sometimes you take less risk, and it seems that I have said that when you take much risk, it seems that you have to label it as pejoratively ad hoc. But that is not necessarily the case, because pejoratively ad hoc means that you have tried the solution and got epistemic harm. You tried the solution and obtained not a good result. So that is reason to call the alternative and move to something else. While pejoratively ad hoc descriptively ad hoc, is pursued under conditions of ignorance of theoretical structure. It is different to ignore something that to already have been harmed by something. Does that make your question solved?
Yeah, let me press you a little bit on the epistemic harms that we might face, because my concern is that sometimes they are not so visible as epistemic harms. So they might be part of the results of what we are modifying, and we know they might not be true necessarily, but that doesn't mean that we agree upon saying, oh, they are leading us to false belief or to something worse than that. And so is this a concern that you have thought about how saliently the epistemic harms have to be in order for us to recognize them when we are making the detection?
Yeah, thank you. What I think is that the list that I have given is not exhaustive. In fact, yeah, there are other epistemic risks that can be taken into account, but I think that the epistemic risks that I have presented are at least illustrative of what epistemic risk one can take when holding an ad hoc hypothesis. And yeah, if you claim that a great part of cosmology is done in an ad hoc manner, I would partially agree on that too. And I think that it is not a bad feature. It is a feature of a growing science. What I think is that we can assess how much risk you take on holding an alternative, but that, yeah, only retrospectively you know if it was rational to pursue such an alternative. Yeah, because only retrospectively can you assess whether it has whether it granted unificatory power, coherence, etc. The theoretical values that I have mentioned.
Thank you very much, Andres. And if there are no more questions here, there are no more questions on YouTube either. So let's thank Andres with a round of applause. Oh, Sergio, no, we cannot leave. So Sergio has a question. Please, Sergio.
I'm sorry, please don't kill me.
No, we have
Andres,
still 8 minutes, so don't rush.
okay. Andres, thank you very much for the presentation. Just one question that arises from it is like a curiosity of mine, and it concerns to the limits of the ad hoc modifications of a theory. So my question is, where do we find the limits in which there could not be any more ad hoc modification. I mean, we find a phenomena that it just requires us to leave a theory, right? Is there a limit? Do you see a clear limit for that, or we could just simply add new hypotheses?
Yeah, thank you for the question. Know that in my account of ad hocness, sorry, I was reading something else. I will run into that later. Yeah, so your question is there a limit for including ad hoc modifications? I think depends on what type of ad hoc. Pejoratively, ad hoc modifications should be cut, or at least maybe not cut at all, but a deep reassessment of the idea has to be taken seriously, right? Yeah, my claim is that pejoratively ad hoc may fall into the rejection range or either into the entertain range. That is also an attitude that scientists can take towards a theory or a research program. In principle, I think that we do still need we still need many ad hoc modifications on the dark matter research program and also on the modified gravity research program in order for them to be sufficiently robust. So to clearly answer your question, we can still modify it ad hocly in principle, as long as, and not only to include these ad hoc modifications, but also to rationally pursue them as long as it retains the theoretical virtues that I've mentioned. If it starts somewhat to degenerate, to stagnate, when that may be a reason to leave the research program. And the question is, the multiverse hypothesis is pejoratively ad hoc. I don't know. Maybe you can talk us about that so that we can decide if it is descriptively ad hoc or pejoratively ad hoc.
So, next in way, do you want to follow up on this? Do you want to extend? Yeah, sure.
That's okay. I'm just out of curiosity. I just want to hear Andreas' opinion of whether he thinks that that's okay. Thank you.
Right. I don't know. Well, in order for the hypothesis to rely on the pejoratively ad hoc range, it had to have done us some epistemic harm. And I do not know. I mean, I have to confess, I am not very well informed of these hypotheses. I really wouldn't know how to answer your question. But the fact that it would not fit into the pejoratively ad hoc hypothesis might be a limit of my epistemic signal, right? Yeah, good one.
Yeah, that's okay. Thank you.
Thank you, everybody. And now we are on time to close this session. Thanks, Andres. And please give him a round of applause, reaction, and just clapping. And now we are going to have a 10 minutes break, and we are coming back for 2 more contributor talks before today's session ends. So see you in 10 minutes.